And I will talk about our work with Sebastian at Cologne University and also Xiaoqi from MPQ. And we will talk about topological response in open quantum system. So let me explain to you what I have in mind for open quantum system. We will imagine we have an open quantum system here, which is surrounded by some dissipating environment. And in some setup like the optical cavity, people might even turn on some external drive there. So I have a laser turning on. And the system here will always interact with the environment. And this will lead to some exchange of symmetry charge or maybe energy with the environment. And this open quantum system, understanding them is very important for our quantum technology. For example, we want to have some quantum simulator. Say we have some ultra cold atom. And this one is basically we set up some optical lattice and we trap some cold atom there. And this cold atom will always interacting with the environment. And also, we might have some programmable quantum simulator. Say I have a readable atom, and we can have really high control of this atom there. And this one will, of course, interacting with the surrounding environment. And even more broadly speaking, we can imagine our quantum computer is an open quantum system because it will always interacting with its surrounding environment. And this kind of engineered quantum system will give us some new ingredient in the sense that it's highly controllable. So it will give us some new preparation strategy for different kind of quantum matter. It will always also give us some new tool, which is beyond the traditional many-body physics. Say in the condensed matter case, we like to measure local observable like density or conductivity or things like that. And now we can really have access to some non-local observable. And I will give you some example here. The first one is some quantum microscope. So I can prepare some BEC. Say here's some BEC gas here, and then I can have a microscope which can image out with a high precision of the distribution of each atom there. And then after some reconstruction, I can really know the distribution of each atom. And by preparing this thing and doing measurement for many times, I can really reconstruct the whole probability distribution of the particles at position. So in this way, I can now have access to the position distribution and even higher cumulant, which is also beyond the traditional approach. Another thing is that now I can also prepare some highly entangled state, say the quantum spin liquid. The idea is that here I have some product state, say atom living in the link here, and then by evolve the system with some unitary operator, then in the end I will obtain some dimer here. By dimer, I basically mean I have a Bell's pair here. And it will become a superposition of this kind of Bell's pair. And this one is a quantum spin liquid. And people can really benchmark the existence of this wave function by measuring the string order parameter, which is non-local. So it's beyond traditional approach. Another thing is that now we can further prepare long-range correlated state. Say I have some quantum circuit here, and then I apply some unitary operator and also some measurement. And in the end, I can obtain maybe some Nishimori criticality or things like that. So far so good, but the problem is that this one are open quantum system in the sense that we will always have some decoherent noise. And this leads to some new challenge. First of all, now we need to consider mid-state instead of the pure state scenario. Another thing is that when we talk about symmetry in open quantum system, the notion will be different. The first one is the so-called strong symmetry. By that I mean the symmetry operator here acting on the density metric, it will give us a phase factor. And physically speaking, this basically means there's no symmetry charge exchange with the environment. And let me explain to you why the physics is like this. We can understand this one as a canonical ensemble if you like step back. So I can rewrite the density metric in terms of some pure state here. And A is labeling different pure state. And when I have the symmetry operator acting on this pure state, it will pick out a phase factor. And this one is more or less the symmetry charge associated with the symmetry operator. But this symmetry charge doesn't depend on the state. So all the state in the ensemble will have the same symmetry charge. So that's basically the canonical ensemble. Another notion is the so-called weak symmetry. So I have a symmetry operator acting on the density metric. And here, there's no phase factor there. And physically speaking, this means we have symmetry charge exchange with the environment, but you will conserve on average. So that means we are now talking about grand canonical ensemble, if you like StatMech. So again, I write the density matrix in this way. But now, when I apply the symmetry operator to the eigenstate here, you will pick up a phase vector, a symmetry charge, but depend on the label of the state here. So now the state can exchange the charge with the environment, but on average, it will be fixed. So these two notions means we have different ensemble, generally speaking. However, in reality, the strong symmetry is generally more restricted. As we see, this one will require every state to to have the same symmetry charge, and it will generally require fine-tuning in experimental platform. Another thing is that this symmetry is also fragile in the sense that we will, for most of the case, we will have strong to weak symmetry, spontaneous symmetry breaking. Say I starting from some canonical ensemble, and then I evolve that with some symmetry preserving Lindblad equation or operator. In the end, the steady state will break the strong symmetry to weak symmetry. And that's something we know, right? In StatMech, we like grand canonical ensemble. Because of this, we can ask the question, are there new physics in this kind of new setup? And the question we try to ask here is that for topological phase protected by symmetry in open quantum system, are there any new phase, or how to understand that? And this comes to the outline of the rest of this talk. So first of all, I will remind you the symmetry-protected topological phase in the pure state limit. And then I will attend to the mid-state case, but I will consider two scenarios. One is with at least one strong symmetry, and another one is with only weak symmetry. Then I will apply this to a concrete example and showing you that there is some intrinsic topological phase protected by weak symmetry only. And as a many-body physicist, I will always focus on order parameter. I like to talk about quantized response, string order parameter, something like that. And why we are interested in symmetry-protected topological phase, for the quantum information community is useful resource state for quantum computing. And as a many-body physicist, I would like to think of there as some exotic phase of matter, in the sense that in our textbook of StatMech, we say we have order parameter, which is always local operator, like the density for the spin-liquid phase transition, or for the liquid and solid phase transition. And here we require non-local order parameter to really see the topology. And two of that is the quantized response. Another one is the string order parameter. And they turn out to be actually the same. And I will walk you through below. So let me explain these two concepts in the AKLT state. So the AKLT state is given as follows. I have this one is a spin chain, and this one for spin 1/2, this one for spin 1/2. And the blue plaquette here is for the projector onto the spin triplet. Because there's a spin triplet, so I can label the state by the spin component of the spin 1 representation. And the line here is for the projector onto the spin singlet. And if you like MPS, then, or I will introduce you below, is that this one can be understood as a matrix in this way. This one is for the physical lattice, that's the spin 1, and this one for some virtual bond. And we can now rate out the A matrix here. So first of all, this one is for the projector onto the spin triplet. And this one is for the spin component equal to -1. So this one is the spin down in this spin 1/2 representation. And this one is for the spin up, and this one for the spin up and spin down. And the Y here is from the projector onto the spin singlet. So you know this one is spin up and spin down. This one is also spin up and spin down. And importantly, this state has some symmetry there, which is the pi rotation along the z-axis. Say here, this one is some global on-site symmetry. So I have a tensor product N here, means I will apply this symmetry onto all the sides of the spin chain. And similarly, I have a pi rotation along the s-axis. And in terms of the MPS representation, that means if I have the metric product state here, I apply a physical symmetry here. That's the pi rotation. I can actually pull that to some, compensate that in terms of some symmetry acting on the virtual bond here, and up to a irrelevant phase factor. So for AKLT state, the important property, from the SPT perspective, is that first of all, we have some symmetry here. We can pull the symmetry to the virtual bond. And if we would like Hamiltonian, then this one is the spin 1, like the hold-down chain. And then I will want to characterize this phase in terms of order parameter. The first one I'm talking about is the quantile response. By that I mean I take the ground state wave function of the AKLT chain, and I insert a flux here. By flux, I mean I imagine I have a one-dimensional chain here. And just like the AB phase we learned from quantum mechanics, if I drag the spin here along the chain, you will pick up a phase factor or symmetry transformation applied by the phi x here. So here is for the flux equal to pi, and here is for no flux. And then I want to study the symmetry charge. So this one is the global symmetry acting on all the sides. And I'm saying about quantile response to flux insertion. That means I considering the ratio for the charge here with flux and without flux. Another understanding is that in the MP, so this one is a physical understanding. I want to get rid of the, in comparison to the no flux state. In terms of MPS, we know there's an irrelevant phase factor here. And this phase factor should be cancelled by this denominator here. And here, the value for the AKLT state is equal to -1. It's negative for topological phase and positive for normal phase. And in terms of the MPS representation, we can clearly see that this topological charge is actually related to the group cohomology invariant. And I will show you below. So in the MPS representation, the symmetry charge here will acting on the ground state wave function. And the flux insertion is given by the virtual bond here. So you can imagine if I spin here, I drive that along the spinning chain, it will obtain a phase twist by this kind of symmetry operation. So that justifies its meaning as a flux insertion. And again, just using the standard technique, we can pull through the physical operation to the virtual bond. And so that means this RZ here is replaced by the sigma Z, sigma X, and sigma Z. And this one, they anti-commute, so we will find our -1 here. We can actually make this one more systematic and mathematical. And there's something done before. One can show that this quantile response here, -1 here, is actually related to the second cocycle of the group cohomology in this way. So it's invariant. One can show that it's invariant under the gauge transformation. And we want to talk about another one, is the string order parameter. I'm making the following claim. The topological invariant will imply a selection rule in the string order parameter. So let me explain to you what I mean here. So by string order parameter, I mean I have a ground state wave function A here, and then I create a symmetry twist domain. By twist, I mean I apply a symmetry operator here. And also I create an untwist domain. By that I mean there's nothing insert here. And then in between, there's the domain wall separating the symmetry twist domain and untwist domain. I decorate the domain wall with a symmetry charge. So by symmetry charge, I mean the chi L will have the following transformation law. It will pick up a phase factor. And now the string order parameter, one can show that it will vanish if the quantile response is not equal to the symmetry charge of the domain wall. So it can be non-zero only if they equal to each other, in turn. And also a side remark, mainly for Esper, is that when I say the string order parameter vanish, I always mean the leading eigenvalue of the transfer matrix. That's a side remark. So this is what I mean by selection rule for the string order parameter. And we show that here, the quantile response actually connecting, this one non-local observable and also the string order parameter. They are just the same, at least for pure state. So let me make a quick summary, and then we will move to the mid-state case. Now we have identified the topological phase via some non-local order parameter, which is the quantile response and the string order parameter. And the key symmetry property for the SPT here is that we have this following transformation of the MPS. And there is a different perspective, is that people can also define phase in terms of the equivalent class that for state that can be connected by a finite depth circuit, which will preserve the symmetry here. And for pure state, they are the same. One can prove that. But for the mid-state, they are not necessarily the same. And in the rest of this talk, I will, more or less take a many-body physics approach. I will take the order parameter approach. And I will comment on the different approach later. So now let me move to the mistake in open quantum system. I want to have a tensor network representation, and let me want to apply the Klaus operator here to a density matrix, which is basically modeling the interaction between a system and the environment here. And so in terms of the tensor network, for presentation simplicity, I made the following assumption, that I only apply on-site decoherence. By that I mean I have a wave function here, and then I introduce an ancilla here. And the Klaus operator can be rewrite in terms of a unitary operator. And this approximation is known as the locally purified density operator. So now we have a pure state representation of the density matrix. And the key ingredient for this kind of tensor network representation is that we still have a matrix product stay here, but the price to pay is that in addition to the physical side, I have also an ancilla here. So this one is the key ingredient I will focus on in the later of the discussion. And also, I would like to make a side remark is that now we only focus on the simplest version of the tensor network, but we can apply our result to general matrix product density operator, but with strong injectivity as well. So, but for simplicity, I will always focus on the LPDO. And then I want to discuss about symmetry in this representation. And the first one is, of course, the strong symmetry. And I assuming an on-site global symmetry. By on-site, I mean it will apply to all the sides of the spin chain. And this strong symmetry implies a canonical ensemble. That means there's no symmetry charge exchange with the environment. And in terms of the MPS representation, that means the ancilla here is charge neutral under this symmetry. So when I apply the symmetry operation to the physical side, I can push through to the virtual bond here with the irrelevant phase factor. And then I can also compare that with the wave symmetry case. We know in this case, we have symmetry charge exchange with the environment, but it will conserve on average. And that means the ancilla now is charged under this symmetry operation. So to push through the symmetry operator, I need to apply on both the physical side and also the ancilla. So here's the key difference between the strong symmetry and wave symmetry in terms of this MPS representation. And this is the key identity I will use in the rest of this talk. So do you have any questions? Just feel free to interrupt me. Then I will move on. I will consider the case with at least one strong symmetry. That means I assume the ancilla here for the strong symmetry is neutral. So the symmetry I consider is the strong symmetry and also the wave symmetry here. So by strong symmetry, I mean the ancilla is charge neutral. And by wave symmetry, I mean this ancilla is charged under the symmetry operation. And then I want to consider the order parameter for this phase. And the first one is the quantum response here. And again, I have a denominator here. It's because we want to consider the response to flux insertion. So I need to mod out the one without flux. And if you like MPS, that's basically saying I just get rid of this irrelevant phase factor here. The charge here is a strong symmetry charge in the sense that every state in the density matrix will have the same charge. So we expect, intuitively, the thing will just be the same to the pure state case, and that turned out to be true. I will show you. And also, I have applied a wave symmetry flux. So by that, I mean I have a Hamiltonian or maybe density matrix on this chain, and when the particle winding around the chain, you will pick up a symmetry transformation. And in terms of the MPS representation, this quantum response is given in the following way. And one can prove that this wave symmetry flux insertion still apply for this MPS representation. And here is the strong symmetry charge. So we realize that everything are basically in parallel to the pure state case. And we expect the same thing will be true for both the quantum response and also the string order parameter. And I will show you how that works. And the key identity here is that the strong symmetry can be pushed to the virtual bond. So the thing is that now I use this kind of push-through identity. The symmetry charge here can be pushed to the virtual bond here. So I have a VG dagger. And this one is actually the invariant in the group cohomology here. And this is a result obtained before. So now we found that the quantile response here is actually classified by the group cohomology. And then I want to show you that the same thing still applies, is that quantile response will imply the string order parameter, the selection rule there. The thing is that this symmetry domain wall will lead to a selection rule. This string order parameter will vanish if the quantile response and also the symmetry charge of the domain wall doesn't match. Another thing is that this symmetry twist domain will have an order 1 because we can push through the symmetry operator to the virtual bound. And now let me make a summary here. We consider the case with both strong symmetry and weak symmetry, and we can take the strong symmetry charge response to weak symmetry flux as an order parameter. And this one can lead to a classification by the group cohomology here. And it can also lead to a selection rule in the string order parameter. However, as I mentioned before, the strong symmetry is generally fragile or maybe more restricted, which require fine-tuning and also will have some spontaneous symmetry breaking. So I want to ask the following question. Can the weak symmetry alone protect non-local order parameter? And this comes to the rest of this talk. I will looking at only with weak symmetry. And as a reminder, by weak symmetry, I mean the ancilla here is charged under the symmetry operation. So to push the operation here to the virtual bound, I need both the physical side and ancilla to have a symmetry operator acting there. However, the challenge here is that now I cannot use the push-through identity like we used for the strong symmetry case. And the answer turned out to be yes. We can still have some quantized response there. However, the price to pay is that nowadays this one is not necessarily classified by the group cohomology, but it's remain quantized as we can prove that. So this is the price to pay, and I'm not sure about the mathematical structure behind so far. So now I will consider the case with both weak symmetry G and weak symmetry H. And I will consider the tensor network answer the locally purified density operator. And as a side remark, I would like to emphasize that our result can apply to general metric product density operator, but with some strong injectivity applied to that. And the result is based on the following observation. I can have a transfer matrix here with symmetry twist here. But still, the flux insertion operator will commute with this kind of transfer matrix. So one can prove that this one will equal to this one. So I have a commutation relation. And because of this commutating relation, one can show that the quantile response here is actually an eigenvalue of the flux insertion operator. And this flux insertion operator will form a representation of the finite group here, so it will remain quantized. So let me show you how. So one can find that the quantile response can be represented in this way. So as a reminder, the RG0 and LG0 is the leading right eigenvector and left eigenvector of the transfer matrix. And because I'm assuming the leading eigenvector is always larger than the subleading, so I can keep the leading term here, just like we do in standard metric product state technique. And because of this commutating relation, this one will be an eigenvalue of the flux insertion operator. From here, we conclude that we can obtain some symmetry with symmetry protect non-local order parameter because it's an eigenvalue of the flux insertion operator. And to change the quantile response, I need a gap closing. So that means I have a transfer matrix here, and the leading eigenvalue and the subleading eigenvalue will be 0 to change the quantile response, say exchange of the leading eigenvector. And if you lie that mad, then this one is basically saying I have a Lie 0 to separate different phase. In the sense that this UG is a unitary operator, and this one is a positive definite operator. So I can imagine this one as some imaginary external field. So by adding this external imaginary field, then this one is basically what Li and Yang have done for STANMAT long ago. And now let's move to the string order parameter. And I made the following claim. If I'm in the non-trivial phase, by that I mean non-trivial quantile response, then the selection rule still exists in this phase. The reason is as follows. again, the string order parameter here, this is the wave function, and this is the symmetry twist domain, and this one is the untwist domain. And this is the domain word separating two domains. And we can rewrite this part in terms of the following way. And this part is actually, as one can show, the eigenvalue of this flux insertion operator. And it has eigenvalue of its symmetry charge. And this one is the right eigenvector, leading eigenvector of the transfer matrix here. And its eigenvalue is the quantile response. So we conclude the following selection rule here. The string order parameter will not vanish only if they have the following match between the quantile response and the symmetry charge of the domain word. However, still we have a price to pay here. Is that in this regime, we know it will give us the eigenvalue of the leading eigenvector of the transfer matrix, something behave like this. And for strong symmetry, this one will have order 1 because we can push the symmetry operator to the virtual bound. And then it will equal to the one without symmetry twist by a unitary transformation. So the leading eigenvalue is always of order 1. However, for this wave symmetry case, we cannot push through to the virtual bound. So this one will generally be smaller than 1. And as we know, this part will have a decay of the distance, of the string distance, but still is coming from the leading eigenvector of the transfer matrix. So if we can know the leading eigenvalue, then we can actually normalize this one to 1. Introduce a normalization here. By doing so, this one will have an order 1. But let me remind you that there's something people have done, but in a different context in the topology order. So people will consider the torical, which have some Z1 form symmetry, and then they can have some string order parameter, the Freden-Hagen-Markov string order parameter there as well. And however, if we turn on external magnetic field, which break the one form symmetry, and in that case, even that's a topology order, then one cannot see that in terms of a string order parameter, unless we normalize that in this way. So that's basically what I'm doing here. I have a string order parameter, and I normalize it. But that's in a different context. So I can make the following conclusion. For a strong symmetry and the normalized string order parameter, I have selection rule and order 1. However, for a wave symmetry case, we need to normalize the string order parameter. In this case, we can also obtain the selection rule and the order 1 of the string order parameter. And I think the highlight of this one is that in both cases, the decaying of the string order parameter is from the leading eigenvalue of this one, of the transfer matrix. So from this perspective, they are the same. So I can make the following summary here. With only wave symmetry, I can see a quantile response, and also we can see a selection rule in the string order parameter. And so that means non-local order parameter does exist in the wave symmetry case. And the phase transition will happen if I have a degenerate spectrum in the leading eigenvector of the transfer matrix here. So I have a gap closing concept in this kind of transfer matrix, and which is something cannot happen in the strong symmetry case on the pure state case. And this one is more or less like the Leon zero for this context, in the sense that this symmetry operator will more or less inserting an external imaginary field to the system. And then let me explain to you in this context with a concrete example. And the goal of this part is that, assuming I have some phase of matter here with phase 1 and phase 2, I want to turn on the coupling between the system and the environment. And then I ask, can I find something new? Can I find some phase can appear only in the mid-state case? And the answer turned out to be yes. So here's the model we consider. So we're still starting from the AKLT state, and we have some symmetry pi rotation along the x, y, or z axis. And then we turn on on-site Clausen operator. And this one is for the spin 1 operator, and one can check that it will break the symmetry, it will preserve only the wave symmetry of the system. And the other parameter we consider is the quantile response. By that I mean the RZ rotation symmetry, wave symmetry to RX flux insertion. Another one is that I consider the symmetry charge to RY flux. And there are there are other symmetry charge as well, but they are not independent because some group structure in the system, in the symmetry. And here's the result. P is for the error rate of the system. And if the error rate is below 1/2, then I see the AKLT phase. By that I mean they have the same quantum response to the AKLT state. And now I want to increase the error rate here. And now I found that this quantum response to Y flux will change here. And this is something cannot happen in the strong symmetry case, and also the pure state case. And the reason is that if I'm looking at the transfer matrix, then you will have a gap closing here, as I advertised before. And then I want to consider the normalized string order parameter. And here is a string order parameter in the regime, and here's in this regime. And we does see a qualitative different behavior distinguishing these two phases. And here come to the, so we have confirmed our result by using this concrete model here. So now I confirm that if I turn on the interacting between the system and the environment, then I can find some new phase there. So also by new phase, I always mean order parameter. And so this comes to the conclusion here. For weak symmetry, I found that it can protect the topological response in open quantum system. And by that, I mean the quantum response and the string order parameter. And also, there can exist some intrinsic phase protected by weak symmetry, which does not have a pure state or strong symmetry analog. And here's the conclusion I want to make in this talk. And there's some interesting open question. First of all, in fermions, say in one dimension, we can find some similar behavior of the phase transition there. And the thing is that the phase transition is signaled by the loss of one H mode, topological mode there. And there's something different from traditional approach of the thermodynamic phase transition. And so it will be interesting to see if we can have a tensor network approach for higher dimension or system, or maybe a bosonic or fermionic system. And there is also a connection between the quantum error correction and this kind of phase transition. By that I mean, we can imagine a toric, and then we can formulate that to obtain some Majorana phase transition. That turned out to be some finite temperature system. And the phase transition, the decoding phase transition, say I add in B-flip or phase error there, turned out to relate it more or less like disorder or interaction for the Majorana. And the phase transition of the toric just signal the loss of two logical qubits, and which is captured by the topological invariant, the quantized charge response in the case we discussed before. And so the highlight of this one is that in this case, we are basically looking at the loss of the topological protective mode in the system. And final outlook is that it might have possible connection to MBQC. The reason is that, as we know, the string order parameter is actually from the leading eigenvector of the symmetry twist transfer matrix. And this one might or might not give us a Bell's pair-like behavior for the two-domain work on the end. And that's something to look into in the future. And then finally, as I promised before, I would like to comment on the definition of phase. So here we define that in terms of order parameter, but another approach is from more quantum information perspective, we may ask that are there any quantum channel connecting this phase? And for mid-state case, generally speaking, these two approaches are different. So here, yeah, this come to the end of my talk.